Hi, in this video I will share IGNU MCA's new 4th semester assignment questions for the subject MCS to 3.0, Digital Image Processing and Computer Vision for the session July 2024 and January 2025. The first question is, what is image acquisition? Explain optical, analog, and digital image processing in brief. Image acquisition. Image acquisition refers to the process of capturing an image, typically from a physical scene, through an imaging device like a camera or scanner. This is the first step in the workflow of image processing, where the physical light energy from the scene is converted into a digital form that can be processed by computers. The quality and characteristics of the acquired image are crucial as they form the foundation for subsequent image processing tasks. The first one is optical image processing. Optical image processing involves manipulating images using optical techniques rather than electronic or digital means. This method often uses components like lenses, mirrors, and light sources to process images. Examples include holography, capturing and reconstructing the light field to produce a three-dimensional image. Optical filtering, using physical filters to enhance or modify certain features of the image, such as edges or patterns. Fourier optics, utilizing the principles of Fourier transformation in the optical domain for image analysis. Second one is analog image processing. Analog image processing deals with images in their continuous form. This involves manipulating the image signal without converting it to digital form. Analog techniques were more common before the advent of powerful digital computers and include methods like electronic filters, using analog electronic circuits to filter specific frequency components of the image. Photographic techniques, applying chemical processes to film to enhance or modify images, such as developing and printing photos with different exposures. Analog video processing, manipulating the signals in video formats like VHS or Betamax for tasks like signal enhancement or noise reduction. The third one is digital image processing. Digital image processing involves converting images into a digital form, a matrix of pixel values, and using algorithms to manipulate this data. This is the most common and versatile form of image processing used today. Key areas include image enhancement, techniques like histogram equalization, contrast adjustment, and noise reduction to improve the visual appearance of an image. Image restoration, removing imperfections or distortions from an image, such as blurring or noise. Image compression, reducing the file size of an image for storage or transmission, using methods like JPEG or PNG compression. Image analysis, extracting meaningful information from images, including tasks like edge detection, segmentation, and pattern recognition. Machine learning and AI, applying sophisticated algorithms to understand and interpret images, used in fields such as medical imaging, facial recognition, and autonomous vehicles. Conclusion. Each of these processing methods has its applications and relevance depending on the requirements of the task at hand and the technology available. The second question is, if the physical size of a medical image is 4 inches and the sampling resolution is 5 cycles or mm, then how many pixels per cycle are required to have a better quality image? Will an image of size 512 be enough? To determine if an image of size 512 pixels is enough for a given sampling resolution and physical size, let's go through the necessary calculations. Given data, physical size of the image, 4 inches. Sampling resolution, 5 cycles or mm. Steps to determine pixels per cycle and total pixels required. Firstly, convert physical size to millimeters. 1 inch equals 25.4 millimeters. Therefore, 4 inches equals 425.4 millimeters equals 101.6 millimeters. Secondly, determine the number of cycles in each dimension. With a sampling resolution of 5 cycles or mm, the number of cycles in one dimension 4 inches or 101.6 millimeters is number of cycles equals 5 101.6 equals 508 cycles. Thirdly, calculate pixels per cycle. A high-quality image typically requires at least 2 pixels per cycle. Based on the Nyquist sampling theorem, which states that you need at least 2 samples per cycle to accurately represent the signal without aliasing. Pixels per cycle 2. The fourth step is to calculate the total pixels required in each dimension for 508 cycles, with 2 pixels per cycle. Total pixels equals 5082 equals 1016 pixels. The fifth step is to determine if 512 images is enough. The required pixel resolution for a high-quality image is 1016 pixels. Given an image of size 512 pixels, we can compare it with the required 1016 pixels. Clearly, an image size of 512 pixels is not enough to meet the high-quality requirement derived from the sampling resolution of 5 cycles or mm for a physical image size of 4 inches. For high-quality representation, the image resolution should be at least 1016 pixels. Explain the types of images based on eye attributes. 2. Based on color. Types of images based on attributes. Binary images. Description. Binary images consist of pixels that have one of 2 possible intensity values, typically 0 black and 1 white. Usage. Often used in image processing tasks like edge detection, shape recognition, and document scanning. Grayscale images. Description. These images contain shades of gray, with pixel values ranging from 0 black to 255 white for 8-bit images. They do not include color information, only intensity. Usage. Common in medical imaging, for example X-rays, satellite images, and any application where color information is not necessary. Color images. Description. Color images are composed of multiple color channels. The most common format is RGB red, green, blue, where each pixel is represented by 3 values corresponding to the intensities of these primary colors. Usage. Used in photography, television, computer graphics, and any application requiring realistic images. Indexed images. Description. Indexed images use a color map palette to store colors. Each pixel value is an index pointing to a color in the color map. Usage. Efficient for images with a limited color range, such as graphics and web images. Multispectral and hyperspectral images. Description. These images capture data at multiple wavelengths across the electromagnetic spectrum, beyond the visible range. Multispectral images typically have a few discrete bands, while hyperspectral images can have hundreds of contiguous bands. Usage. Used in remote sensing, environmental monitoring, and agriculture for detailed analysis of the Earth's surface. 3D images. Description. 3D images. Volumetric images include depth information for each pixel or voxel volume element. These images are not just confined to a 2D plane. Usage. Common in medical imaging, for example MRI, CT scans, and 3D modeling. Types of images based on color. RGB red, green, blue images. Description. The most common color model, where each pixel is represented by 3 values corresponding to the intensities of red, green, and blue. Usage. Widely used in digital cameras, monitors, and various display systems. CMYK cyan, magenta, yellow, key or black images. Description. A subtractive color model used in color printing. It represents colors through the combination of cyan, magenta, yellow, and black inks. Usage. Used primarily in printing industries to create full-color images on paper. HSV hue, saturation, value and shell hue, saturation, lightness images. Description. These color models separate color information hue from intensity value or lightness and saturation. They are more intuitive for human understanding of colors. Usage. Useful in image editing, graphic design, and computer vision for color manipulation and recognition tasks. Index color images. Description. These images store color information in a palette and use an index to reference specific colors. The image data contains indices to this palette rather than direct color values. Usage: efficient for images with limited colors, such as icons, logos, and GIFs. Grayscale images. Description: although not traditionally considered a color image, grayscale images represent intensity variations without color. Each pixel's value ranges from black to white. Usage: common in applications where color is not critical, such as medical imaging and document processing. YUV and ICBR images. Description: color spaces used in video compression and broadcasting. YUV separates luminance Y from chrominance UV, while ICBR is a digital form used in video compression standards like JPEG and MPEG. Usage: essential in video processing and transmission to efficiently encode color information. Lab color space. Description: a color space that includes all perceivable colors, organized in 3 channels: L lightness, A green to red, and B blue to yellow. Usage: used in color management systems for consistent color reproduction across different devices. The conclusion is understanding the types of images based on attributes and color models is crucial for selecting the appropriate methods and tools for image processing tasks in various applications. The next question is, what is the storage requirement for a 2024 x 2024 24-bit color image? To calculate the storage requirement for a 2024 x 2024 24-bit color image, you can follow these steps. Firstly, calculate the number of pixels. The image has a resolution of 2024 x 2024 pixels. Total number of pixels equals 2024 equals 4,096,576 pixels. Secondly, determine the bits per pixel. The image is 24-bit, meaning each pixel uses 24 bits, which is equivalent to 3 bytes, since 1 byte equals 8 bits. Thirdly, calculate the total storage requirement. Storage requirement equals number of pixels bits per pixel. Convert bits to bytes. 24 bits equals 3 bytes. Total storage equals 4,096,576 pixels. 3 bytes pixel total storage equals 12,289,7 to 8 bytes. Final answer. The storage requirement for a 2024 x 2024 24-bit color image is approximately 11.72 megabytes. Calculate pixel resolution of a camera in megapixels, capturing an image of dimension 3000 times 4000. The answer is to calculate the storage requirement for a 2024 x 2024 24-bit color image. You can follow these steps. Step 1. Calculate the total number of pixels. Image dimensions 3000 times 4000 pixels. Total number of pixels equals 3000 for 1000 equals 12 million pixels. Step 2. Convert to megapixels. 1 megapixel MP equals 1 million pixels. Megapixel resolution equals 12 million pixels. 1 million equals 12 MP. The final answer is the pixel resolution of the camera is 12 megapixels. Given an image is a grayscale image with an aspect ratio of 8:2 and pixel resolution of 1 million pixels, calculate the dimensions and the size of the image. Given the following information, the image is grayscale. The aspect ratio is 8:2. The pixel resolution is 1 million pixels. We need to calculate the dimensions, width and height, and the size of the image. Firstly, determine the aspect ratio. The aspect ratio of 8:2 can be simplified to 4:1. This means the width W is 4 times the height H. Let width W equals for X. Height H equals X. Secondly, calculate the dimensions. Given the total number of pixels, WH equals 1,000,000 pixels. Substitute W equals for X and H equals X into the equation. 4x x equals 1,000,000. 4x square equals 1,000,000. X square equals 1,000,000 is divided by 4. 250,000. X square equals 250,000. X equals skirt to 50. 000 equals 500. So, height h equals x equals 500 pixels. Width w equals for x equals 4500 equals 2000 pixels. Thirdly, determine the size of the image. Since it is a grayscale image, each pixel requires 1 byte 8 bits for storage. Total number of pixels equals 1 million pixels. Total size in bytes equals 1 million bytes.